So welcome back. This is our third video about sampling, and now we're going to discuss the Gibbs sampling. So let's take a look on this slide here. We're going to have one explanation about the Gibbs sampling, and in the next slide, we're going to look at one example. So the procedure is the following. Let's keep track of a full instantiation x1, x2 until xn. So these x1, x2 are the variables. So this is one first difference from the methods that we saw before. So the methods that we were working with, they never worked with full instantiations. They started instantiation the variables one by one, starting by a trivial assignment. So now we're going to work with the full instantiations. We start with one full instantiation and starting making changes to this instantiation until we get the sample that we want. So we start with one instantiation that is consistent with the evidence. That's good. Sample one variable at a time, conditional to all the rest, but keep evidence fixed. And keep repeating this for a long time. So this long time is quite imprecise, and we're going to see later that it is related to the mixing concept for Markov chain. And there is a property that if we keep repeating this process, the resulting sample will be coming from the correct distribution. All right, we're going to see this later, but this corresponds to the idea of the stationary distribution for Markov chains. So what is the rationale? That both upstream and downstream variables conditional on evidence. And that is an interesting point because we didn't have that with the likelihood sampling. But now, because we're going to work with those complete instantiations, with some variables instantiated to the evidence, and we're going to change the values of the variables one by one, we have now the possibility of changing one variable, like a root variable in the Bayesian network, based on other variables that are instantiated. So we will have this upstream influence of the evidence going up in the Bayesian network. So in contrast, the likelihood weighting, that was the last method that we discussed, only conditions on upstream evidence. And consequently, the weights that are obtained by likelihood weighting can sometimes be very small. The sum of weights over all the samples is indicative of how many effective samples were obtained, so we want high weights. So we're going to change now with Gibbs sampling is the fact that we will not have weights anymore. So now it's like every instance we'll have the full weight back again. And we need to know how we're going to compute this, and we're going to show you in the next slide. So here we have a summary of how to compute the Gibbs sampling. We need to start with the evidence, and we fix the evidence. Let's suppose that we want to compute this query here, the probability of S given little r. So we set the evidence that's going to be r equal to little r. So we have this evidence here, and we're going to express the true values with a green color and the false values with the red color. And we go to the second step that will initialize all the remaining variables. So I'm going to give values for the remaining values. So we need to decide how to do this, but for instance, we could give random values for each variable and continue. There are better options than this one, and we're going to discuss later on in the next slides. So now that we have this complete instantiation, I'm going to start and change the instantiation variable by variable. So it's important that as we gave these random values, this instantiation does not come from the probability distribution expressed by the Bayesian or the Markov network. It's just a random evidence. It's just a random instantiation. So we need to start and change this in order to make it to follow the distribution expressed by the network. And the way that we do that is by choosing one variable at random and changing the value of this variable according to the value of all the remaining variables that we have in the network. So for instance, let's suppose that we choose a variable s. we're going to only change the variables that are not evidence. We're going to keep the evidence fixed. So we're going to choose those variables that are no evidence variables, right? So S is a no evidence variable, so I choose S to start. It was randomly chosen, and now I'm going to sample the value of X given by this distribution here. So the probability of S given the values of C true expressed here, W false expressed here, and R true expressed here. So just ignore this plus sign here. It is meaningless for our example here. And note that we don't have this conditional probability distribution readily available in the network. And this is one difference of the given sampling compared with the previous methods. Every time that we had to sample according to a conditional probability with the first three methods that we studied, those conditional probabilities were the parameters of the Bayesian network. So we just went there and took the value. So we could sample in a very efficient way. We didn't have to do any inference in order to make the sample. And now we will have to do inference. And we're going to discuss how we can compute this in the next slide. But I can anticipate that for you, that this inference is going to be very efficient. So we sample the value for S, and let's suppose that we sample S equal true. So I did not change, no, actually I changed it because it was false here. So I will change now S to true. And I go to the next variable. Again, I choose a variable at random. Let's suppose that we chose the variable C, and I will sample a value for C according to this distribution here, right? And we see that the distribution is specified by all the values that we have in the network. So it's going to be S true, W false, and R true. So I sample this. Again, we don't have this conditional probability readily available. Is not one of the parameters of the network. We can look at the network here, right? And it's not one of the parameters, so we have to do a little bit of inference in order to compute this. And we sample again, and let's suppose that we sample the value true for C. So we keep that, so we didn't change C, and we go to the next one. Again, we chose a variable at random. The variable that we chose is now W, and I'm going to sample W according to this distribution here. It's again the distribution specified by W given all the variables instantiated in the network. So we have S, we have C, and we have R. And I'm going to sample now, and let's suppose that we sample the value false for W. So we didn't change it. And we keep on doing this for a longer period of time. So we saw in the previous slide that in this situation here, we had to make a sample according to this conditional probability here. And we don't have it, we need to compute this. So how do we compute this conditional probability? So let's take a look on the equations and see if we can figure out what are going to be the factors that we need to multiply in order to compute this. So we have this probability that is a conditional probability, P of S given C, R, and not W, that are going to split this into a joint probability, the probability that mentions all variables together, C, R, so this is the big S, and not W, and this is divided by the probability of C, R, and not W, right? Okay, now we want to factorize this according to the chain rule of the Bayesian networks, but before doing this, I will need to include the variable S in the bottom part here. So it's going to be S, C, or not W, and here we can make the sum over S, the probability S, C, R, and not W. Alright, so we now are in position to expand this according to the chain rule of the Bayesian network. So we know that is going to be the probability of the little c times the probability of the big S given the little c times the probability of the little r given the little c times the probability of not w given the big S and the little r. And that's going to be divided by this sum here. So it's going to be the sum over S of the, again, little c times the probability of, not going to be the little s, but this little s will assume the two values, true and false. C, the probability of r given c, and the probability of not w, s, and r. Okay, so we can move out this guy here. It does not depend on s. This guy here does not depend on s. So we'll have the probability of c, the probability of the big S c, the probability of a little r c, and the probability of not w, s, and r. This is going to be divided by probability of c, the probability of r given c, and this sum over s, the probability of s c, and the probability of not log s and r. Good. And now we can cancel. So we can cancel these two terms, and we can cancel these two terms here. And what we got is the following. It's going to be the probability S given C and the probability of not W, S, and R over the sum over S, the probability of S given C times the probability of not W, S, and R. So if you look at this expression here, we can see that actually what we have in the denominator is a normalizing constant. That we can ignore. So this guy is going to be proportional to the probability of S given C times the probability of W, S, and R. So basically what is happening here is that we cancel out all the factors, all the CPTs that do not mention the variable that we are sampling. So now we can have a very efficient sampling because we're going to multiply just the factors that mention the variable that we are interested in sampling, and also because all the entries will be instantiated but the entries for the variable S. And we haven't seen this before. Actually, it's the same thing that happened when we were classifying one instance according to the Bayesian network. We had a very similar situation where we wanted to know what was the most probable value for a class attribute that was not instantiated based on the values for the other variables that were all instantiated, because we were working with the complete instantiation. We were working with the complete cases. So that's going to be the same thing, right? So we just need to multiply the factors that mention the variable that we're going to sample. At the same time, the entries of these tables will be fully specified, just not for the variable S. So we're going to have to check just what's going to be the values for the variable X. And that's going to be a very efficient type of inference. Okay, and we have talked so much about Bayesian networks. It's very good to know that we can use the Gibbs sampling in Markov networks. And let's take a look at one very small example to see that what we saw about the efficiency efficient inference that we can do for Bayesian networks is also true for the Markov networks. So we have again our voted example, and let's suppose now that you want to sample a value for the variable a, and we have specified that b, c, and d have a true value. So again, we have to compute this probability of a given b, c, and d, and this is going to be equal to, and we can use the Gibbs distribution. It's going to be 1 over the partition function, the p tilde, that is the unnormalized distribution, and now we're gonna make a and b and c and d, and we're going to divide it by the probability of just the evidence here. So it's going to be 1 over the partition function, the probability of b, c, and d. So one good news here is that we can get rid of the partition function right away, so we can continue just with the unnormalized distributions. So in this case, we have the p tilde of a, b, c, and d, and now we're going to introduce another variable that's going to be the variable a. So we're going to sum over a here, the p tilde of a, b, c, and d. Okay, now it's a good time to introduce the Gibbs distribution. That's going to be the multiplication of the factors. So we're going to start with the phi1, going to be over variables a and b, times the phi2 over variables b and c, times the phi3 over variables c and d, times the phi4 over variables a and d. Going to be divided by the sum over a of the same factors. So it's going to be the phi1 ab, the phi2 bc, the phi3 cd, and the phi4 ad. We have factors that do not depend on a, this and this guy here, that can take it out. So we're going to be again phi1 ab, phi2 bc, phi3 cd, phi4 ad, and the factors that I can remove, phi2 bc and phi4 phi3 cd, and the sum over a for the remaining factors, phi1 ab and phi4 ad. Good. We can cancel this guy, this guy, this guy, and this guy, and what remains is phi1 ab, phi4 ad over what's going to be a normalizing constant that is over the same factors. Right, so this is proportional to phi1 ab, phi4 ad. So you're going to be very efficient again. You only need to multiply these two factors. We have the variables b and d instantiated. Only the variable a is not instantiated, and we need to see what's going to be the probabilities for each value of a. We compute that, and we can sample a using those values. So it may be hard to believe in the beginning, but the Gibbs sampling is a Markov chain. And you should remember the Markov chain. We have a lecture about this class of dynamic Bayesian networks. It's a very simple type of dynamic Bayesian network that we have the nodes and we have these iterations over time here. And these nodes, they represent an initial probability. So we start here with the probability P0, and we're starting to iterate over this, and we have the probability of the state is going to change over time. And we keep doing this and applying the forward algorithm, and we saw that after a certain number of iterations, this probability here would converge to a stationary distribution that we call it the pi. We also specified here what was as a very important part of this idea, the transition probabilities. So basically the transition probability is the probability of xt given xt minus 1. And these transition probabilities are very important because they will define what's going to be our stationary distribution pi. Now imagine the following, that we can start with a random assignment for values of the Bayesian network. So we can start with this probability here, P0, that can be very different from the final probability here. But if we choose the correct transition probabilities, we can get into the probability, the stationary probability pi that we want. And that is exactly what the Gibbs sampling does. What we do here is to think about the Bayesian network as a huge state space. So each state in this state space will be a complete assignment for the network. So imagine the size of this state space is going to be exponential in the number of variables. So we start with one assignment, right? One complete assignment here. It doesn't mean that this complete assignment will be of the stationary distribution that we are looking for, but we're going to start to apply these transition probabilities. These transition probabilities, they are specially designed in a way that the stationary distribution pi will be equal to the probability distribution specified by the Bayesian network or the Markov network. So the central ingredient of this algorithm is in fact the transition probabilities here. And if we iterate long enough, our initial assignment will start to converge to this stationary distribution. So one important point here is to find out when we have reached the stationary distribution. When we have reached the stationary distribution, we can start sample from this distribution and use those samples to answer queries that we are interested on. So this is the summary. So we want to compute a certain query, a certain probability for variables x. However, the probability distribution P may be too hard for us to sample directly. So one case that happens is when we want to sample from x given some evidence E, but E is very small. So we're going to reject several samples, or we're going to do the likelihood weighting and we will come out with a very small weights. So what we're going to do is something different. Instead of sampling from this distribution here, I'm going to sample from a different distribution. And the distribution that I'm going to sample is the transition distribution specified by the Gibbs sampling algorithm. And we saw which distribution is that. Is a distribution that we want to sample a certain variable x given all the other variables that we have in the network instantiated. And we saw that we can make this sample in a very efficient way because it's going to involve a small number of factors, and the factors will have all the variables instantiated, but the variable that we're going to sample. So we are transforming the problem of sampling from a difficult distribution into another problem that we're going to sample from an easy distribution. And that is a very important part of the Gibbs sampling. So we're going to construct a Markov chain T, whose unique stationary distribution is the distribution P that is induced by the network, the Bayesian or the Markov network. So we saw from the Markov chain lecture that in order to this distribution to be unique, the chain has to be irreducible or regular, right? So this condition will guarantee to us that the stationary distribution is unique. So we start sampling from a different distribution that we call P0 that is different from P, right? I don't care about this. So for instance, we can start by assigning random values to the values of the variables. That's not going to be the true distribution, but we're going to start to iterate that. We're going to start transitioning this Markov chain until it gets to the stationary distribution. And when we get in the stationary distribution that we call the pi in the Markov chain lecture, we can start sampling from this distribution and building our database of samples. And that is the most difficult part of using the Gibbs sampling, is to find when our Markov chain has reached the stationary distribution. So the idea is that we want to sample from the chain when the distribution has reached the stationary distribution. So usually at the early iterations PT, we are far from the distribution P that we are interested. So we need to wait to the chain to converge to the stationary distribution. Basically, we continue sampling the values and continue sampling the values. We call this state that the chain has reached the stationary distribution the mix. So we say that the chain has mixed. And it basically means that our current probability distribution is close to the stationary distribution pi. And we are ready to start sampling. But that is a difficulty because there is no test that will guarantee to us that we have reached this mixed state. But I'm going to postpone this discussion to the next video. So let's take a break now and we continue with Gibbs sampling in the next video. See you soon.